nanohub.org.
Okay, so let's get started. I'm going to show some demos of what I had just shown in the lecture. So if you go to nanohub.org, you see this web page, and there's major highlights on the left about simulation, research, teaching and learning, how to contribute, and then some nano networks that we're connected to. If you click on the simulate, there's a list of supported tools that we really care about a lot, meaning we have support personnel that answers questions and is committed to supporting these tools. The other tools are contributed by the community. So here you see a list of tools, and the tools that are here, you can sort of scroll through. If you wanted to know what this tool, the commitment is to our supported tools, you can click on this link here, and it basically states that we will answer any questions, or try to answer any questions that you might have within a business day, and we'll try to fix small bugs within a week, and larger bugs or larger wish list items we move into a public wish list that we maintain. So if I now go into this tool called Resonant Tunneling Diode Simulation, I can click on here, and I can get a brief outline. It's simulates 1D RTDs using NEGF. It's an NCN supported tool. And if I click on this link here, I get to the tool page. And the tool page gives me a little bit more details on who helped writing this code, so who are the authors. There's some screenshots of things you can do with this tool. So here's a screenshot. And there's a sort of the synopsis of how many people have utilized this. So 249 users utilized this tool. They ran some 4,600 simulations, and on average it takes 2 minutes to compute. I'll make this a little bit bigger. There's questions that are being asked. There's reviews. There's 5 wishes that have been added for tool improvements. This tool has not been cited yet in the literature, so 0 citations. And there's a variety of versions that have been published and improved. And down here you can see sort of a list of features and the upgrades from the previous versions, some of the theory references, how you learn about this, and then tool limitations, then the credits, and then some citations we suggest you read. And if you do use this code for research, we ask that you cite it in this form. Okay, so that sort of gives you an overview what you can do. And if I click on this launch tool, it's going to launch the tool. And if you haven't logged in, it would ask you to log in first, put in your login name, etc. And this is how the tool shows up. So let's look at let me do this. You can, by the way, pop out this. This is a Java-like window, but as I mentioned before, it's not a Java applet. The tool itself, it actually runs on the Purdue backend, but it looks like a Java applet here. You can actually pop this out over here, so you just get an independent window that you can move around and also rescale. So here's a simulation with RTD NEGF on a very simple resonant tunneling diode. We have specified a potential model that is a linear drop. That means as we apply a voltage, the potential drops linearly like this. And we've chosen a quantum well at 7 nanometers and chosen an undoped spacer of 0, 0. And in the advanced tab, we've turned the relaxation in the reservoirs off to 0 millectron volt. So here, I'm ramping on the left and right here through the voltages, and you can see how the central resonance in the middle here is being pulled through the sea of electrons indicated by the Fermi level and the conduction band edge And as I increase the voltage further, there's no supply function, there should be no transmission, and I'm starting to pull the second resonance down into the sea of electrons. You can see this in a schematic, also in the resonances versus voltage plot, where you see the resonance being pulled in the, down linearly in the ground state, and here's the excited state resonance. It's pulled into the sea of electrons, and here's the conduction band edge. So you expect current to flow within energy ranges above here, voltage ranges above here, and the current should not flow once the resonance is under the conduction band edge. So now we can look at the current voltage characteristic. You indeed see a current flow that increases and then decreases, and it increases again because the second resonance is already being pulled into the sea of electrons, and it becomes relevant. And you can now show this also with a transmission coefficient as a function of bias. And here you see it. We can change the energy scale. Here, let's just go, since there's never any current flow for energies below zero, we can just look at the energy range here. So here's this transmission coefficient, and as I ramp up the voltage, I'm pulling the resonance out of the energy range of relevance, and I'm pulling the second resonance down, and eventually I see some really broad resonances, some shoulders here, that are being pulled into the conduction range. And eventually also the center resonance 2 goes away. And you can also look at the normalized current density. Zero current, you have no current. But here you see the current density. And here you see the integral over the current density in green. And you can see even at a very small bias of 0.01 volt, there's already about 90% of the current here flowing in the second state. And as I ramp this up further, you see more and more current flows in the second state, and then the ground state goes away, and all of the current is flowing through the second state as you ramp up. And once the second state starts to move away, you're just conducting through these broad shoulders, which means current is flowing in over a broad energy range. Okay? So that ultimately results in a current voltage characteristic that looks like this. The next question you need to ask, why is this peak here much smaller than this peak here? And that has to do with the resonances and their width. So here is a more busy plot. Again, here you have the the central resonance going down, and the second state going down. But here's the resonance energy of the lowest resonance. It's roughly 10 microelectron volts thick in energy, and the second state has a resonance energy that's a factor of 40 larger. So roughly there's a factor of 40 more current flowing through that resonance, which corresponds reasonably well to the current voltage characteristic, which is quite different from here to here. Okay, so that explains roughly the current flow in a RTD that has a linear potential drop. Okay, so those are the fundamentals.